Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutewa Sos Ugobela Maths. And without any further ado, let's look at this question paper that we have here. Okay, so we have the Western Cape Metro Central Education District question paper, Physical Sciences Physics Paper 1. September 2024. So as we can see, the date was written on Wednesday, 4 September 2024 for 3 hours and marks 150. They say this question paper consists of 16 pages and 3 data sheets. Right, so you will go through the information. I hope you went through the information and instructions during your exam. And now let's just go straight to our multiple choice questions. It says question 1, multiple choice questions. 4 options are provided as possible answers to the following questions. Each question has only one correct answer. Choose the answer and write only the letter A to D next to the question number 1.1 to 1.10 on your ruled A4 paper, for example, 1.11 D, right? So if you fill your option to 1.1, for example, is A, then you can just select A. Now, okay, 1.1 says a wooden block is pulled up a rough inclined surface using a rope. The wooden block moves at constant velocity. So we have our keyword there, constant velocity. And then you will remember what we said about constant velocity. So this means that A, there are no forces acting on the block, not quite. There are no vertical forces on the block, not quite. Only gravitational force acts on the block. That would have to be free fall. That's not what we are talking about here. The vector sum of all forces acting on the block is equal to 0. So if it's moving at constant velocity, we know that our F net is equals to 0 because first our acceleration is 0 meters per second square. Then we have the formula F net is equals to ma. So if our acceleration is 0, then also our F net is 0 newtons. So D here would have to be correct. The vector sum of all forces acting on the block would have to be equal to 0. So our option is, we want to write here. So this is how you're supposed to write it in an exam. So we want to have 1.1 and then we have D, right? Okay, now let's proceed. We have 1.2. It says the mass of an object is on Earth is represented by X over G. Which one of the following represents the mass? So they even wrote it in bold, of the object on a planet that is twice the mass of the Earth and half the radius of the Earth. Now this here is all to confuse you. Now you must know one fundamental fact is that the mass of the object does not change depending on which planet it is in. The only thing that changes is the weight, because the weight is simply a product of the mass and the gravitational acceleration of that particular planet, right? So but then the mass, if something is 80 kg on planet Earth, even if it goes to planet Mars, it is still 80 kg. Then even if it goes to planet Jupiter, it is still 80 kg. The mass does not change because it represents the quantity of matter in that particular object. But then the weight obviously would change because we would take the mass multiplied by the gravitational acceleration of that particular planet, of which we do understand that the gravitational accelerations are not the same. So here, if this has a mass of X over G on Earth, that means even on another planet, it still has to have a mass of X over G. So here, your solution was just supposed to be B. Right, so a little question just to confuse you then. Now 1.3 says ball A of mass m is projected vertically upwards from the ground with an initial velocity v, and then ball A rises to a maximum height h above the ground. Ball B of mass half m is now projected vertically upward with an initial velocity of 2v. Ignore the effect of air friction. Now, in terms of h, to what maximum height does ball B rise above the ground? Now, the first thing that we want to do, let's try to calculate for ball A. So we are just trying to compare this in terms of h. So for ball A, if we were to look for the height, we would go and choose the formula Vf squared, Vi squared plus 2a delta y. Right, now our Vf, because it reaches the maximum height, we know the velocity final at the maximum height is 0, and then this is 0 square. The initial velocity, they say at velocity v, so we're going to have v squared there, and then 2. Now the a here, it's supposed to be negative 9.8. Let me not substitute it, I'll just substitute negative a, because we know that it will always be a constant. Then I'm just going to leave the delta y there, right? Okay, so if I were to then bring this over here, this will be 2a delta y, and then is equals to v squared. So I'm trying to write this in the format of delta y. Delta y, the subject of the formula. So this is 2a. So my delta y here would have to be 1 over 2 v squared, and then over a, right? So just like that. Now that would be for ball A, right? Now if I were to indicate the same thing for ball B with the same formula Vf squared, Vi squared plus 2a delta y, my Vf, remember it reaches the maximum height as well, so 0 square. Then the initial velocity, they said, however, the initial velocity for this one is 2v, right? So we have 2v squared there. And then our acceleration, I'm still going to substitute it as negative a, because we know it's supposed to be negative 9.8. If I'm taking upward as positive, I'm going to say delta y here. And then again, I bring this over here. This is 2a delta y. And then here, this will be 4v squared. Again, if I make my delta y the subject of the formula, this is divided by 2a. So my delta y here, 4 divided by 2, will be 2v squared over a. Right. Now, if I have to compare this, this is my height initially for ball A. Then I want to compare it with the height for ball B. Right. So let's say this indicates height of A, ball A, and then this indicates the height for ball B. Right. Now, what is the simplified ratio to this? So what is the simplified ratio to this? Obviously, we'll deal away with the v squared over a, because they are the same both sides. And then if I were to look for the simplified ratio here, if I divide both sides by half, this would be 1:4, right? So that means the height of ball A to the height of ball B is actually 1:4. So that means which one is the correct answer here? If the height for ball A is considered to be h, then the height for ball B needs to be considered to be 4h, because the ratio means that the height reached by ball B is 4 times the height that was reached by ball A. So that means our correct option here has to be D. So 1.3 is D. Right. And then let's go. Now we have 1.4. It says an object of mass m moving at velocity v collides head-on with an object of mass 2m moving in the opposite direction at velocity v. Immediately after the collision, the smaller mass moves at velocity v in the opposite direction and the larger mass is brought to rest. Ignore the effect of friction. Refer to the diagram below. Now they say which one of the following regarding the momentum and kinetic energy of the system is correct. Now we know in all cases, the momentum is always conserved, whether it's an elastic collision or an inelastic collision, we know that momentum is always conserved. So B and D would have to be incorrect. But then what about the kinetic energy here? Now, given this collision, we can tell that this is an inelastic collision because we are told that one of the masses here, they will move in the opposite direction, but then the other mass is brought to rest. So that means kinetic energy is not conserved. So here in option A, they say kinetic energy is conserved, which would be incorrect. But then in option C, we can see they say kinetic energy is not conserved. So this one is correct. So our option here would have to be C. Okay, then let's go to 1.5. They say the graph below represents a constant force acting on an object over a displacement x. The force and the displacement are in the same direction. Which one of the following statements can be deduced from the graph? The gradient of the graph represents the work done by the force. Not quite, because as we can see here, this is just a horizontal line. And our knowledge of maths tells us that the gradient of a horizontal line is always equal to 0. So that would not be representing the work done by the force, because the work done by the force here is unfortunately not 0. Right? So the gradient of the graph represents the change in kinetic energy of the object. Not even close. So A and B, completely incorrect. Then the area under the graph represents the net force, the net work done by the force. Definitely correct. Because if we can just try to calculate the area here, this is length times breadth, right? So obviously it would be F multiplied by delta X, which if you are looking for your formula for work done, that's F delta X and then cos theta. Considering that our theta here will be 0 degrees, this cos 0 degrees is equals to 1, which leaves us with only F delta X, and then here it's 1, which is just W is equals to F times delta X, which is what is being represented by this. So if we were to calculate the area under the graph, what would actually get is the work done by the net force. So C here would have to be correct. Is the area under the graph represent the power? Definitely not the power, because the multiplication of the force and the displacement does not represent power, but actually represents the work done, right? Note again, if you go back to the definition of what is work, we say work is the product of the net force and the displacement. Okay, so that means C here would have to be correct. Now 1.6, a car travels at constant velocity along a horizontal road. A constant frictional force acts on the car during its motion. Which one of the following statements about the power dissipated by the engine of the car during the motion is correct? Now, is the power equal to 0? Not quite. Does the power increase? Nope. Does the power decrease? Nope. Does the power remain constant? It has to remain constant, because also here we get that the car would be traveling at constant velocity. So if it's moving at constant velocity, that's an unchanging acceleration. So this acceleration is 0 meters per second square. So that means your power is just remaining constant there. So for 1.6, we'd say your option is D. 1.7, light reaching the Earth from a galaxy moving away from it is shifted towards a greater velocity, a higher frequency, or a longer wavelength. If we explain the concept of, so this here we are being told it's moving away. So they say a light reaching the Earth from a galaxy moving away. Remember, this is suggesting that the universe is expanding. And the theory that suggests that the universe is expanding is known as the redshift, right? In the redshift, what we are explaining is that as this is happening, we can see that the light that is coming from the galaxy moving away would have to be moving to the longer wavelength, right? So to the longer wavelength. So obviously with a longer wavelength, that means the frequency is becoming smaller. So this here is just a 10. Most of the time we are used to having it is moving to lower frequencies, right? So we know with the redshift, it's moving to lower frequencies. But considering the relationship between frequency and wavelength, we know that with the lower frequency, we have a longer wavelength, right? So if we are talking about the redshift, the expanding of the universe, we say this is when the light is actually moving to the lower frequencies, but then lower frequencies actually means a longer wavelength. So as it is moving away from the Earth, remember, if it's moving away, then that means we're expecting a longer wavelength. Then 1.7, the option has to be C. Now, two charges of positive 2 nanocoulomb and negative 2 nanocoulomb are located on a straight line. S and T are 2 points that lie on the same straight line as shown in the diagram below. Right, so they say which one of the following correctly represents the direction of the resultant electric field at S and T. So if they're talking about electric field, that means we must take a point S and T as the positive point charges. So if we say this is a positive point charge, and also there is a positive point charge. Now, where will S move due to this one here? So direction of the resultant electric field at point S. Now, as we can see here, S, because of this one is a positive and a positive, will be repelled towards that direction. But then again, this is a negative, causing it to be attracted towards that same direction. So for the direction of the resultant electric field at point S, this would have to be what? Right. So we see right for option A and option C. Now, let's go and check for point T. Now, for point T, we can see that point T is closer to this negative 2 nanocoulomb here. So obviously, it has to be attracted because it's positive and this one is negative. It has to be attracted towards that, right? So that means it is moving where? It is moving to the left. So which option is saying left? It has to be A there. So that means now we have 2 dots on A. So A is the correct option. So for 1.8, we are going to say A. Now let's go to 1.9. It says the circuit diagram below shows 4 identical bulbs, M, N, and P, and Q connected to a battery. The power dissipated in bulb M is 60 watts. The resistance of the connecting wires in the battery may be ignored. Then they say the bulb dissipated, the power, meant to say the power dissipated in bulb Q is it A 0 watts, B 15 watts, C 60 watts, or D 120 watts. Now we know that our current will be moving from the positive terminal all the way to the negative terminal. But if we reach this point here, we can see here there is a form of a short circuit here, because now considering that this is only a connecting wire here, and then right here we have our bulb Q. Now we know that current always takes the part of least resistance. So our current will always favor to go to the part where the resistance is very, very low. So at this point, we know that the connecting wire has negligible resistance, which is a very low resistance or no resistance at all. So we know that most of our current will now be diverted to go through this direction. And then we'll have to split over here to go to either a bulb P and then split to that other direction to go over to a bulb N and M, right? So considering this, that means there will be no current that actually flows to Q. And if there is no current that flows to Q, according to P is equals to I squared times R, if our I is 0, that means our P has to be 0 watts. Why? Because this is a short circuit here. They simply put in a connecting wire here, which will make the current not to go to Q here, right? Because the current will take the part of lower resistance. So our perfect solution there is A. So for 1.9, we have to say it is A. Now we have 1.10. It says the diagram represents 3 energy levels, X, Y, and Z, in a certain atom. The energy difference between levels Y and X is twice the energy difference between levels X and Y. If the wavelength of a photon emitted as a result of transition P from level X to Y is lambda, then the wavelength of the photon emitted during transition Q from level X to Y has to be A, 2 lambda, or 3 or B, 3 lambda, or C, half lambda, or D, 1/3 lambda. Now you have to understand that the more we go down here, obviously this is moving from an excited state to the ground state. And then this here is an emission line spectrum, right? So with an emission line spectrum, the energy is what? Released. So there's energy released. Now we do understand the relationship. If we are to break down this, we know that the relationship between energy and frequency is directly proportional, right? But then now we are trying to talk about wavelength. So that means we can break this down to this, and then we find that actually the relationship between energy and wavelength is now inversely proportional, right? So that means with an increase in energy, we have a decrease in the wavelength. Now, if we are saying energy is released, that means when it's moving from that excited state down to the ground state, it is increasing in energy as it is releasing most of its energy. So if the wavelength from this part to this part is lambda here, and then we are expecting our energy to increase as this moves from X to Y, that means from the point whereby it's now coming over here, remember we are being told that at this point here, this is twice, right? So they said the energy difference between levels Y and Z is twice the energy level. So let's say here we have 1E, and then here we have what? 2E. So all of this from X to Z should be 3E. But then if we are saying that the relationship here is inverse, if we have 3E, that means what is it that we must have for our lambda? It must be an inverse of this. So what is an inverse of 3? Obviously, this is, if we say 3 to the exponent of 1, this is going to give us 1/3, right? And then it's supposed to be 1/3 lambda. So the more we increase in energy as we are going down, that means we have to actually decrease in wavelength. So that means our correct option here would have to be option D, right? Because at this point, the energy will be 3E, but then what must happen to the wavelength? The wavelength must be a reciprocal of that, which is 1/3 lambda. So 1.10 here is supposed to be option D. That's how you could have went about answering your questions for the multiple choice, right? So all of that for 20 marks. Remember, the advice is you always have to just tackle your multiple questions as the last question, because multiple choice questions can be time consuming, guys. So you need to be very strategic when it comes to this. Either if you are answering question 2, you are answering questions on Newton's second law, you can go and check for multiple choice questions only on Newton's second law. You answer those, and then when you move to momentum, you only answer multiple choice questions on momentum, and just like that, you'll be done with your multiple choice questions in a much easier and strategic manner than having to spend maybe 30 minutes or 40 minutes trying to figure out the options to this, right? So, okay, let's now start with our question 2, which is Newton's second law. Okay, so we have question 2, and we know it's Newton's second law of motion. It says 2.1 block M1 of mass 8 kg placed at point X is connected to block M2 by a light inextensible string passing over a frictionless pulley. Block M1 is on a plane inclined at an angle of 30 degrees to the horizontal and experiences a frictional force between points X and Y only. Block M2 has an unknown mass and moves vertically downwards as shown in the diagram below. And then right there on the diagram, below the diagram, we have yet another statement. It says block M1 is released at point X and moves at constant velocity. So note that whenever we see this keyword, I always made you note that it means that acceleration is 0 meters per second square. But then because of this formula, F net is equals to m times a, which is the Newton's second law formula, we know that if acceleration is 0, then it follows that our F net should be 0 newtons as well, right? The coefficient of kinetic friction acting on the 8 kg block between points X and Y is 0.2. So we are given the coefficient there. And another thing that you should note, if we are given coefficient of kinetic friction, we know that there's somewhere where we need to calculate the magnitude of the kinetic friction. So always have that in your mind. Then 2.1.1 says state Newton's first law of motion in words for 2 marks. So let's run quickly to that. We know that our definitions should always be 3 marks to us. So the body states that the body will remain in its state of rest or motion at constant velocity unless an unbalanced net force acts on it, right? So for 2 marks, that's how you should define Newton's first law. The body will remain in its state of rest or motion at constant velocity unless an unbalanced net force acts on it, right? Then consider the motion of block M1 between X and Y. Draw a label-free body diagram indicating all the forces acting on block M1. And then for 4 marks, 4 marks means we have to have 4 forces. So what I always like to do is resolve the components of the gravitational force so that I can clearly see all the horizontal forces and vertical forces taking part there. Then this is my normal force, and straight in line will always be my FG perpendicular, and then always sliding down the incline is my FG parallel. It's always sliding down the incline. Let me draw it properly there. So there we go. You have FG parallel, and then up here we must have our tension force, so Ft. But then remember, we are told that there is a coefficient of friction here, so obviously that means we also have a frictional force, Fk. So now how many forces are here? When we count here, this is how we do it. So those are the marks. This is a normal force, tension force, and then these ones are marked as one because they are components representing the gravitational force. So 3 and then 4. Now, if you don't prefer having to resolve, obviously your free body diagram would look like this. So I always have questions saying, but say, what if I drew the other one? You still get full marks, right? You still get full marks. So it's just a matter of what you prefer. If you prefer to draw this one, then you can go with this one here. If you prefer to resolve your components, then it's okay. Now, why do I vouch for this one? It's because you get to see all the forces here that are acting parallel to the surface, which are the ones that we are mainly focused on when we want to calculate our F net, right? But then with this one here, it can be a bit tricky because the only forces that you are seeing here that are kind of horizontal are your Fk and your Ft. And then if you don't consider the fact that this is on an incline, you can miss the Fg parallel here, which can cost you a lot. So having to resolve actually helps in the fact that you get to see the Fg parallel and the fact that you need to also include it on your F net formula, right? So which is why I always vouch for this one here. But then if you can only remember that there is Fg parallel and Fg perpendicular like this, then you can always draw that one and then make a mental note that if you have to resolve your Fg into components, it will become like that, right? So 2.1.3 says now calculate the magnitude of the frictional force acting on block M1. So we know the formula is Fk is equals to mu k multiplied by n. Now with this free body diagram here, we can clearly see that our normal force here is equals to the Fg perpendicular. So you see the first advantage of having to resolve your components. Now I can make a mental note to say, okay, n is equals to Fg perpendicular. So that means my n can be broken down to mg cos theta. Right. So where I see normal force, I can just replace by mg cos theta, because from the free body diagram, I can clearly see that the normal force has to be equal to the Fg perpendicular, because these forces here, these perpendicular forces, always balance each other out. Then the mu k is 0.2. And then the normal force, I will say, what is my mass? 8. And then times 9.8. And then, okay, 9.8, and then cos, the theta is for the angle in here, so 30 degrees. So 0.8 times 8 times 9.8 cos 30. When you punch it into your calculator, you get 13.58 newtons. So I want you to note that when we are on an incline, your n is equals to Fg perpendicular, which is mg cos theta. So this only happens when you are on an incline, right? It is not always the case with your normal force, because I made you note that there are 4 different cases to calculate the normal force depending on the situations that you are given, right? Then we have that 3 mark, so we know 3 mark, formula substitution, and the correct answer. It shouldn't be something difficult. Now, 2.1.4 says calculate the mass of block M2. So, okay, this is what I'm finna do. So let me just erase here. And then I am going to draw. Remember, I always made you note that in a case whereby you have a system of blocks, even though they do not require you to draw the free body diagram for the other one, it is always beneficial for you to draw it so as to indicate the forces acting in there, because eventually you will need to use that other block, right, or the information for the other block. As we can see here, we are trying to calculate the mass of block M2, which is this block here. Now, what are the forces acting on block M2? It is only the tension force and the gravitational force. And then because this is moving at constant velocity, it tells us that the upward forces must be in balance with the downward forces. So that means the tension force is equal to the gravitational force. Right, so now to calculate block M2, the mass of block M2, let's just separate this into 2 different equations. So we'll say for block M1, this is what we have. F net is equals to MA. And then this is our positive direction, because we do understand that if this is being pulled downward, or it is moving vertically downward, as they say, that means block M1 has to be pulled up the incline, which makes up the incline being the positive direction, and then down the incline, the negative direction. Now, positive direction is the direction of motion. This is the direction of motion. And then negative direction is the opposite direction of motion. Opposite direction of motion. So whatever forces that are in the opposite direction of motion, they will be negative, and then whatever forces that are in the positive direction of motion will be positive. So that means my equation will be Ft minus Fg parallel minus Fk, and then is equals to Ma. Right, but then remember the acceleration is 0 due to constant velocity. So I can just replace A by 0 there. So I'm looking for the tension force, and then this is mg sine theta, but then I do have the Fk from the previous question. It's 13.58, and then this will be 0 here. Now let me just substitute for here. The mass is 8 multiplied by 9.8, and then sine 30 degrees minus 13, sorry for that, minus 13.58 is equals to 0. Now, if you punch all this into your calculator, not forgetting the negative here, so you'll say minus 8 times 9.8 sine 30 degrees minus 13.58, you will get negative 52.78, which if you transpose it to the right-hand side, that's positive 52.78 newtons. Right. Now that you have the tension, why are we even calculating the tension? It's because you need to understand whenever we have a system of blocks. So in a system of blocks, we always have the same acceleration and the same tension. So that's what you need to understand here. So if we say the acceleration of block M1 is 0, it follows that also the acceleration of block M2 is 0, because they're moving together as a system. It's more like they are one unit. And then if we say the tension on the 8 kg block is 52.78 newtons, then it follows that the tension for block M2 will be 52.78 newtons as well. Right. So note that always with systems, that's what you need to note. Now for block M2, this is what we now have. So it's F net is equals to MA, but then we have established that our acceleration is 0 as well. So we will have Fg minus T is equals to 0. Now if we have 0 here, that means my Fg is equals to the tension. Right. Coming back to this. If it's moving at constant velocity, upward forces are equal to downward forces. Then this is mg is equals to the tension. So let me just write this as Ft so that we are not confused. Ft, right, force of tension. Then what's the force of tension? It's 52.78. And then my mass, so that's what we are looking for, M2. And then 9.8, that one. So 52.78, we can divide both sides by 9.8. And then therefore our block M2, the mass will be 5.39 kg. Right. And then that's what we have there. So our final solution for M2 is 5.39 kg. That's how you were supposed to go about answering that one, for a total of 5 marks. So pretty decent marks for that. Let's now move to the next question. The 8 kg block continues to move past point Y and up the incline. Now note that for this part here, Y going up, they said this is frictionless, right? So this is frictionless. But then here, this was this had friction, as you can see here, it is indicated, but then after point Y, it is frictionless. So they say the block continues to move past point Y and up the incline. How will the magnitude of the acceleration be affected? Write down increases, decreases, or remains the same. Give a reason for the answer. Now, this one is pretty obvious. We know that if it's now moving on a smooth surface, on a frictionless surface, the acceleration would have to increase, right? So our answer there is increases. And then the reason for that, we can say it's because the net force increases since frictional force is absent. And then also we can mention that at that point, acceleration is no longer zero. So it will no longer be moving at constant velocity there. So acceleration is no longer zero. So obviously it would have to increase if it's no longer moving at constant velocity. Okay, now that's it. So note that. Right. Now let's continue. Okay, here we have Newton's law of universal gravitation, which it's also another law that you need to take note of. On a particular day, the distance between the surface of Earth and the surface of Mars was 4.5 times 10 to the exponent of 9 meters. Mars has a mass of 6.417 times 10 to the exponent of 23 kg and a diameter of 6,779 kilometers. Now we see there is a problem here. Our distance is given in kilometers, and then again we are given the diameter, while what we are looking for is actually the radius, right? So we know that the diameter is twice the radius. So if we want to find the radius, it's just the diameter divided by 2, right? So that's the first thing that we need to note. But then let's define this. 2.2.1 says, state Newton's law of universal gravitation in words. So allow me to just define it down here. It says, so to define that, we are going to say everybody in the universe attracts every other body, attracts every other body with a force which is directly proportional, to the product of their masses and inversely proportional to the square of the distance between their centers, to the square of the distance between their centers, centries. Okay, right. So everybody in the universe attracts every other body with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Now, there is a very important statement there, between their centers. So I'm just going to keep the definition here so that we understand what I'm going to do here. Now, 2.2.1 says, calculate the magnitude of the gravitational force. Calculate the magnitude of the gravitational force Earth exerts on Mars. Now, this is Earth. And then as we understand the circumference here, so let's say this is Earth, Mother Earth. And then as we understand the circumference represents the surface of the Earth. And then right here we have mass. right? Now, this distance that we are given here is the diameter of what? Of mass, or of mass. So let's start by finding the radius. We're going to say 6779 divided by 2, right? And then if we can just quickly punch that into our calculator. So that's 6779 divided by 2. This will give us 3,389.5 kilometers, right? So this is the radius. We are happy with that. Now, again, we have another problem. It's in kilometers. So we need to actually convert it to meters. So kilometers, 2 meters. We know that we simply have to multiply that by 10 to the exponent of 3, right? Which if you do here times 10 to the exponent of 3, the radius now becomes what? The radius now becomes 3.3895 times 10 to the exponent of 6 meters, right? Now, this you can see it if you just punch it in your calculator. So if it write it in a simplified scientific form, that's how you're going to have it, 3.3895 times 10 to the exponent of 6 meters. So we are fine with the radius of the mass. Okay, now the distance that we are given, so we are told that the distance between the surface of the Earth and the surface of Mars was 4.5 times 10 to the exponent of 9 meters. Note that this is between the surface of Earth and the surface of Mars. So this is the surface of Mars here, and then this is the surface of Earth. We are given that the distance between the surfaces is only 4.5 times 10 to the exponent of 9 meters. Right, which is correct. It's in the desired SI unit. But then when we read here, it says the distance must be what? A square of the distance between their centers, not between the surfaces. So this is on the circumference, right? This is on the surface. But then here we are looking between their centers. So that means from the center of the Earth all the way to the center of Mars. Now, if we are to understand this, if we are to have a distance from the center of the Earth all the way to the surface of the Earth, what would we call that distance? Now, knowing our geometry, we know that is called the radius, right? And then also here, if we are to have a distance from the center of Mars all the way to the surface of Mars, what would be that distance? It would be the radius. So that means here we would need to add the radius of the Earth and then also the radius of Mars. But then are we given that the radius of Earth is actually a constant that we can find from our data sheet, right? So it is always a value of 6.38 times 10 to the exponent of 6 meters, right? So it's there. You can go and check it up. It's written as RE, and then this is the radius of Earth. So they wrote radius of Earth, and then they give that value. But then are we given the radius of the mass? We were given the diameter of mass, and then we calculated the radius of mass in meters. So we got 3.3895 times 10 to the exponent of 6 and then meters. Meaning now if we have to calculate the gravitational force that the Earth exerts on Mars, we know the formula that we have to use goes as F is equals to G m1 m2 over r squared, where the G here is the universal constant, 6.67 times 10 to the exponent of negative 11. Now, what is the mass of the Earth? Let's start with the Earth. So again, this is another constant. Mass of the Earth is given as 5.98 times 10 to the exponent of 24 kg on your data sheet as well. So 5.98 times 10 to the exponent of 24. Are we given the mass of Mars? There we go. So this is 6.417 times 10 to the exponent of 23, right? So there we go. And then at that point now, we then need to just put our radius square here, which this r here, the distance, this is the distance between the center of this one planetary body to the center of another planetary body, right? So that means we would have to say 6.38 times 10 to the exponent of 6 plus the 4.5 times 10 to the exponent of 9 plus the 3.3895 times 10 to the exponent of 6. And then you square that because it is the square of the distance between their centers. So from center to another center. Now at this point, you can just punch all of this into your calculator and get your answer, right? So when you do that, you get a 1.26 times 10 to the exponent of 19 newtons. And then that's your final answer right there. So that's how you were supposed to approach that question. So that's how you were supposed to approach that question. So the one thing that you needed to note there is that the distance must be from the center of the Earth to the center of Mars. And that's why we had to add the radius of the Earth and also the radius of Mars to the distance between the surfaces. Okay, right. So I hope that made sense to you. Then you can always go back and recheck the question and try to understand it better. Now let's move to question number 3, vertical projectile motion. Okay, so now we have question 3. It says, learners in a grade 12 class launched a model rocket from rest, and then vertically upwards from the ground. Assume that the rocket experiences a constant acceleration for 1.8 seconds to reach a maximum velocity of 29.7 meters per second, right? It experiences a constant acceleration, at which point it runs out of fuel. Ignore the effect of air resistance. The sketch graph below, not drawn to scale, represents the position of the rocket relative to the ground from the moment it was launched until it crashes back on the ground. And then upward direction is taken as positive. Note that upward direction is taken as positive, so we're going to take up as positive as well. Then during which time interval was the rocket in free fall? Now we are told that from point 0 to 1.8, this was moving at constant acceleration, and then at that point it had an engine, right? It had not ran out of fuel, so the engine or whatever it is that's in there, it's propelling the rocket for 1.8 seconds, right? But then after 1.8 seconds, it runs out of fuel. So that means at that point, that's where the free fall starts, right? From here, now the only force that is acting on the rocket is only the force of gravity, bringing the rocket back down to Earth. So that means our free fall, they say during which interval was the rocket in free fall? In 3.1, we are going to say the moment it runs out of fuel from 1.8 seconds all the way to time t2. So at this point here, all the way up until that point, our rocket was in free fall. Then 3.2, calculate the constant acceleration the rocket experiences between 0 and 1.8 seconds. Now it is not 9.8 meters per second, because at that point we are saying it is not only the force of gravity that was acting on the rocket. Remember, there was something that was propelling the rocket upward to move with that constant acceleration. So we want to find out what's that constant acceleration before it started moving in free fall, right? So it is not 9.8. So now let's calculate. How are we going to calculate that? So we can simply use this formula here to say V finally is equals to V initially plus A delta T. Now, why this choice of formula? We are given that it reaches a maximum velocity of 29.7 meters per second, right? So which means this would be our V finally, but then this model rocket was launched from rest, meaning the V initially is 0, right? And then for how many seconds? 1.8 seconds. So we have time, we have V finally, we have V initially, and then we are looking for acceleration. So this one here becomes the perfect formula. V finally, we are going to say that's 29.7, and then it's equals to 0 plus A. Our delta time is 1.8. Then at this point, you only need to say 29.7 and then 1.8A, divide both sides by 1.8. Then your acceleration is just what? 16.50 meters per second. And then to which direction? Up. So our meters square, meant to say, because it's acceleration, and then upwards. Right, so for 3 marks, formula substitution and the correct answer. Right, then 3.3 now says calculate the maximum height h2. So we want to calculate the maximum height h2 here above the ground reached by the rocket as indicated on the graph. Right, so now for that one, this is what we are going to do. Allow me to just label this one here. I will say this is point A from the moment it is released from here. And then this is point B. And then this is point C. And then we'll say this is point D. So what I'm trying to calculate here, it's the height h2. So at point C. So I can then go like this and say, okay, let me just consider the delta y. Let me consider the delta y at point AB, right? At point AB, this is from here all the way to that point, right? And then this here, I will say this is VF squared, VI squared plus 2A delta y. So because this is the formula with our delta y, we do have the V finally, we do have the V initially, and then we just recently calculated the acceleration there. So V finally again 29.7, then square, the VI is 0, and then acceleration, the one that we just calculated, remember at point A to B, it's not at free fall, then 16.50, and then we have our delta y like that. Now all you want to do is this will be 29.7 square, and then is equals to 2 times 16.50, and then delta y. Now we know what to do here. I do not need to punch all of this into the calculator here and break it down. I can just do like this, right? I can just simply do like this, and then therefore your delta y will be equals to 26.73 meters, right? So, okay, now I have that 26.73 meters. Now, remember, we are looking for that maximum height there. So at this point now, I will say, let's try to calculate the delta y between B and C, right? So now at this point, we can say I have found H1. So if I want to calculate here, can say, let me now consider from B to C. So I will say, let me now calculate delta y between points B to C. So this part now. And then again, with the same formula, VF squared is equals to VI squared plus 2A delta y, right? Now VF at this point, remember, it reaches the maximum height. Now what is the velocity at the maximum height? We always know that the velocity at maximum height is 0. So 0 square. Now the V initially will have to be the velocity at time 1.8, which is represented by the final velocity of point AB. So it would have to be the 29.7. So we're going to say 29.7 and then square. Our acceleration this time, remember, we said between 1.8 to T2, it's moving in free fall, right? So that means our acceleration would have to be negative 9.8. Why negative? Because we took up as positive. If you take up as positive, your acceleration is always negative 9.8 meters per second square. Note that. And then we are looking for delta y. Okay, so at this point, what can we do? Let me just take this here and transpose it over to this side. So this is 2 times 9.8, and then delta y is equals to 29.7, and then square. I'm avoiding having a lot of complicated equations, so I'm just going to punch everything into the calculator. Then therefore, my delta y between B to C is, if we punch that into our calculator, that's 45.0046. Let's just keep it to 4 decimal places, and then meters. But then remember, this is from H1. So let me indicate this is from H1 to H2. But then what are we looking for? We are looking for the maximum height, H2, above the ground. At the 0 point there, this is the ground. So that means we are looking for this distance here plus that distance. Now we just got the distance from H1 to H2, and then initially here we got the distance to H1. So that means if we can take this value plus that value, we would have the maximum height, right? So, okay, at this point, we are going to say, okay, to get H2 now, our maximum height is just simply 26.73 plus that 45.0046, and then let's punch that into our calculator. We get 71.73 meters. Okay, so that's it right there. Okay, then let's proceed. We have 3.4 says calculate how long the rocket was in free fall and hence the value of T2. Calculate how long it was in free fall. Pretty interesting question as well. So for 4 marks. And then what can we do with that one? Again, let's indicate this is A, this is B, this is C, and then this is D. Now, if we are to check between B to D here, the whole distance between B to D, this is where we said this is moving in free fall, because we were asked that same question, 3.1. They said during which time interval was the rocket in free fall? And then we said 1.8 seconds to T2, right? So that's between point B all the way to point D, right? So now let's indicate for 3.4, we are trying to find delta T for point B, D, right? So what can we do for that one? We can just simply say delta Y is equals to VI delta T plus half A delta T square, right? Now, if we are looking for our displacement there, we can all agree that the displacement, remember the shortest distance between the 2 points, so the displacement will be indicated by this here. So this would be the displacement in blue here, because remember the distance it covers going to the maximum height will be cancelled out as it comes back here. But then now from this point going down, this will be the displacement. This is the shortest distance between point B and point D. So this will be the displacement. But note that the displacement is equivalent to the height that we got from 0 all the way to H1. Now, what is that height that we got from the previous question, H1? We had found that it is 26.73 meters, right? But then now the displacement is going downward, right? Because the displacement is all the way when it goes back here. So that means since we took upward as positive, then our displacement, since it's going down, it has to be represented as negative, right? So in other words, our delta Y would have to be negative 26.73 meters. Now, there are different ways in which you could have done that. Others could have just calculated from B to C and then from C all the way to that point to CD, right? But then I just chose to take it all at once and then calculate the displacement between B all the way to D, right? So that means I'm going to use this here as my displacement. Now, this is going to be negative 26.73. But then what is the velocity initially? At that point, we said the velocity at B was 29.7. So 29.7. And then we are looking for delta t, right? So delta t plus half. Acceleration, it's moving in free fall, negative 9.8. And then delta t square. Now at this point, we can see that this is leading us to a quadratic format equation. So this is negative 4.9 delta t square. If we arrange it, this is 4.9 delta t square minus 29.7 delta t, and then minus 26.73 is equals to 0. So I simply took all that's on the right and transpose it to the left-hand side. And then now we can see that we can put this in a quadratic equation. So this is negative b plus minus, and then b squared minus 4ac over 2a. Our b is that negative 29.7, and then plus minus b squared is negative 29.7 square, and then minus 4 times 4,9, and then this is negative 26.73, and then over 2 times a is 4,9. Right. Then when you punch it into your calculator, we know that there will be the one that is negative. You immediately cancel that one out. And then what we find is our delta t there, the one that is positive, is 6.8568 seconds. Right. And then we are going to take this and say for T2, now we understand that if this is the time T2, what we just calculated is from point 1.8 all the way to T2, right? But then we want the value of T2. So what we just got here is the time it takes to move from point B all the way to point D. It is not T2. To find the value of T2, we have to consider that this started here. So that means it's 6.8568 seconds. So that's not a 5, seconds. Then plus 1.8. Now that's how we find the value of T2, because note that we did not start from 0, we started from 1.8 seconds. So we also need to add that in order to get the value of T2. So this becomes 8.66 seconds. Right. So that one was a pretty interesting question here. I hope that you understand all that, especially 3.4 with the displacement and how you change the direction of the displacement based on the change of direction of the ball there, or the rocket, right? So make sure that you note that, and then you revisit the question again to make sure that you understand everything. Then 3.5 says sketch a velocity time graph in your answer book for the motion of the rocket from the moment it is fired until it hits the ground. Clearly indicate the following on your graph: the velocity of the rocket when the fuel runs out, and then the value of time T2 when the rocket crashes on the ground. Okay, so the kind of graph that we are going to draw now that we took up as positive is this. So now we know that between 0 to 1.8, your rocket was just moving at a constant velocity. So this is to show constant velocity there. And then here, so let's indicate this was up until 1.8 seconds. But then after that time, it was now in free fall, right? It was now in free fall. So that means we can indicate the free fall there from that point going all the way to the maximum height, and then from the maximum height all the way to the ground. So note that at this point here, this now represents the maximum height. So what was the velocity at time 1.8? We were told that it is 29.7. So 29.7. So let's indicate this is velocity in meters per second. And then here, this is time in seconds. And then what was the time when it reached the maximum height? It was T1. And then what was the time when it went back to hit the ground? It was 8.66 seconds, right? And then here, obviously, 0, because it started from rest. So this is the graph that you should have. So the part number 1 here showing that it was just moving upward at a constant acceleration. And then from this point here, 1.8 seconds, all the way to 8.66 seconds, it was now moving in. It was now moving in free fall, right? So obviously, if you want to find that, so you indicate it like this. Okay, then that's how you were supposed to go about answering that question for a total of 17 marks. So check whatever that you missed there and fix that. Okay, but then now let's go to question 4, which is a momentum and impulse. Okay, now let's look at question 4. It says a pendulum with a bob of mass 3 kg is kept stationary at a height of 1.2 meter above a surface. It is released, and at its lowest point, it collides with a block mass 1 kg, which is at rest on a frictionless surface as shown in the diagram below. Frictionless surface. Ignore all effects of friction. The diagrams below are not drawn to scale. Then 4.1 says state the principle of conservation of mechanical energy. Right, so we know that definition. It says in an isolated system, the total mechanical energy. So the total mechanical energy is conserved. 2 marks, right? Then 4.2 says using energy principles only, calculate the speed of the pendulum bob just before it collides with the block. But then we have our hint here. We have already defined the principle of conservation of mechanical energy, and then we know it is also part of the energy principles. So that is the hint given by the examiner to say that now that you know that the surface is frictionless, and then we've also made you state the principle of conservation of mechanical energy, it might be that you need to use the principle of conservation of mechanical energy in order to calculate. So let's try it out. We will have sum of mechanical energy initially, which is before, is equal to sum of mechanical energy after, which is finally, right? So we want to have mg, height initially, plus half mv square initially is equals to mg, height finally, plus half mv squared finally. Now, what is our mass? 3 kg. So we have 3 times 9.8. And then our height initially of the pendulum bob is 1.2. So they said it was kept stationary at a height of 1.2. Then plus half, our mass is 3 again. But then initial velocity, it was kept stationary. So it has to be 0. And then mass, gain 3. 9.8. We are looking for a height finally. What is it? So at the time when it reaches that point here, the height will be 0 because it will just be on the surface. Then 0. So we are looking for mass final, velocity finally meant to say. Then 3. then VF squared, right? So at this point, you just want to punch this into a calculator. This will obviously be 0. So if we punch this part here, that's a 35.28 is equals to this as well will be 0. So what is half of 3? It's 1.5. And then we have VF squared. Divide both sides by 1.5. We have VF squared is equals to 23.52, which we can then square both sides to get our final velocity, which is 4.85 meters per second, right? So it's the speed, so no need for direction. Okay, so that's it for our 4.2 4 marks. Now they're saying after the collision of the pendulum bob, or after the collision, the pendulum bob has a velocity of 1.8 meters per second, and the block moves up the frictionless curved ramp until it reaches a maximum height. Note that until it reaches a maximum height h as shown below. Assume that no loss of mechanical energy occurs during the collision. 4.3, another free mark. State the principle of conservation of linear momentum in words. 2 marks for free. When I say in an isolated system, states that in an isolated system, the total linear momentum is conserved. Is conserved. So, right, so we were given just 4 marks worth of definitions there for free. Then 4.4 says calculate the magnitude of the velocity of the block just after the collision. We have just defined principle of conservation of linear momentum, so we might just need to use the principle of conservation of linear momentum. So this is a sum of momentum before is equals to sum of momentum after, right? And then when I have our mass 1 V1 plus mass 2 V2 initially, and then here mass M1 V1 finally plus M2 V2 finally, right? Now let's check this one. We're going to take it as the pendulum here, or the bob pendulum, and then the mass 2. So this will be mass 1, and then the mass 2 would have to be the block. So mass 1 is 3, but then obviously the initial velocity will be the velocity now in which it hits the block, which was the one we calculated previously. It was 4.85 plus mass 2 is 1 kg, but then initially the velocity of the block was 0 because the block, we are told that it was stationary. And then mass 1 is still 3, but then velocity finally of the pendulum bob is now 1.8 because they say after the collision, the pendulum bob has a velocity of 1.8. Note that. So initially, when before it hit the block, or just before it collides with the block, it was 4.85. But after it collided with the block, it was now 1.8. Thus, mass 2 is 1. And then we are looking for this velocity here, V2. Now, if we multiply again here, we will have 14.55. Multiplying here is 0. And then let's multiply this one here. That's 5.4. Then plus V2. So our V2 will be 14.55 minus 5.4. Then V2 will be equals to 9.15 meter per second, right? And then they said the magnitude of the velocity. So let's say it goes to the right because it's the velocity. Velocity needs to have both magnitude and direction. 4.5 now for 3 marks is saying calculate the vertical height h reached by the block. So to calculate the height, the one formula whereby we have the height is again the principle of mechanical energy. So for 4.5 we can say sum of mechanical energy initially is equals to sum of mechanical energy finally. Right. Now for this case, so we have mg height initially plus half mv squared initially is equals to mg height finally plus half mv squared finally. Right. But note that this time is no longer for the pendulum bob, it is now for the block. So we are now looking at the mechanical energy as relating to the block, because they are saying calculate the vertical height h reached by the block. So mass of the block is 1, gravitational acceleration 9.8, and then height initially at this point, when it was still here, the height was 0, because as we can see, it was still on the surface there, and then plus half, the mass is 1, but then the initial velocity at that point is 9.15 square. So just after it collided with the pendulum bob. And then is equals to, mass is 1, 9.8, and then height finally, that's what we are looking for. Then plus half 1, what's the velocity at the maximum height that it reaches? So they say it reaches a maximum height h. Now at the maximum height, we know that the final velocity will always be 0. So that means we need to substitute 0 here, so 0 squared. Now 1 times 9.8 times 0, this will just give us 0. So that means we need to punch this into our calculator. Half of 1 times 9.15 squared, this is going to give us 41.86125. And then is equals to 1 times 9.8, that's 9.8 height final. So from multiplying this, we are getting 0 as well. And then 9.8 both sides. We divide by 9.8 both sides. Our height finally is going to be 4.27 meters. Okay, then that's how you were supposed to go about answering that one. So note. So if you made any mistakes, this is your time to take note, and also make sure that you correct your mistakes so that next time it doesn't dribble you. Then 15 marks in the back. Let's now go to question number 5, which is your work, energy, and power. Okay, so now we have question 5. It says a 850 kg roller coaster is released from rest at point A on the track shown in the figure below. It travels along the straight decline section A to B and continues along the curved section B to C, where the brakes are then applied from point C. The roller coaster comes to a stop at D, right? And then which is 50 meters from C. The coefficient of kinetic friction of the track is 0.42, and then they say ignore the rotational effect of the roller coaster's wheel, right? So note that we are given the coefficient, and then 5.1 says state the work energy theorem in words. So 2 marks for free. Work energy theorem in words. We want to say this states that the net work done on an object is equal to the object's change in kinetic energy. Right? So this is coming from the formula W net is equals to change in EK. So if you want to remember that definition, remember the formula from which it comes. So the net work done on an object is equal to the object's change in kinetic energy. So 2 marks just like that. And then again, we have another 3 marks for free. Draw a label-free body diagram showing all the forces acting on the roller coaster as it moves from A to B. And then there's 3 marks, meaning 3 forces, right? So what are we supposed to do? We can start with the incline just to make sure that everything is nice and clean. So we have our normal force, of course, acting in that direction. So this is the normal force. Then this will be our Fg, perpendicular, because I always prefer to resolve. Then let me just make the dot bigger. So sliding down the incline, I have the Fg parallel, so it must always slide down the incline. Right. And then this is going down, so I have to have my kinetic frictional force acting that way. So this will be Fk, this will be the normal force, this will be Fg parallel, and then here I have Fg perpendicular, right? But then again, still mention that if you prefer not to resolve, this is how you will have it. And then your Fk like that. So if you don't prefer to resolve, this is how your free body diagram should look like. So with your Fg here, and then your normal force, and then your kinetic frictional force, right? So either one of this would be correct. And then always remember with this one here, if you are done, just erase the incline. If you are done, just erase the incline. They don't want it there. So yeah. Then nice. Okay, 1.5.3 says calculate the net work done on the roller coaster as it moves from point A to B. So for that, calculate the net work done. So net work done is a sum of all the energies that are doing work on, or the sum of all the forces that are doing work on the object. So they are energies. So W net. If we are to refer back to our drawing here, let's refer back to our free body diagram. So this is what we have. Now looking at this free body diagram here, we can see that the forces that are doing work on this object here, or on the trolley, what is this? It's a trolley. So it's only Fk and Fg parallel. Normal force and Fg perpendicular, they're not doing work on the object simply because they are perpendicular to the displacement of the object, right? So the object is moving down like this. And then as you can see, since your normal force is perpendicular to the surface, it will also be perpendicular to the displacement of the object. So normal force and Fg perpendicular, they are not doing work on the object, meaning we will calculate the work done by Fg parallel and also the work done by Fk. So, okay. For our W net, this is what we want to have. W net will be equals to work done by Fg parallel plus work done by Fk. But then we said that Fg parallel is sliding down the incline. And then if we are saying this is moving down here, this is in the direction of the displacement, so it's 0 degrees. But Fk is acting up the incline, which is opposite to the direction of the displacement, so its theta needs to be 180 degrees. Now we have W net. If we break down this, it's supposed to be mg sine theta delta x and then cos theta plus this. If we break it down, it must be Fk delta x and then cos theta. But then you will remember that we don't have the magnitude for Fk, right? We only have the coefficient. So that means now we have to say W net, and then note somewhere here that our Fk is mu k multiplied by n, which we did observe in Newton's second law that our n, when we are on an incline, it is always equal to Fg perpendicular, which means this is mu k multiplied by mg cos theta, since Fg perpendicular is mg cos theta. Right, so let's say we want to have W net is mg sine theta delta x cos theta plus the Fk here will be mu k mg cos theta and then delta x cos theta. Now, I don't want you to be confused by this theta here and the thetas in there, right? Now, the theta for here and there, this stands for the theta between the direction of the force and the displacement. So mass here is 850, and then G is 9.8. Now sine the theta from here is the one for the incline, 30 degrees. And then our delta x, 200, but then cos what? 0 degrees, because Fg parallel is sliding down the incline, which is in the same direction as the displacement. And then here we have mu k, which is 0.42. Our mass is 850 times 9.8 cos 30 degrees, because it's for the incline. And then delta x is 200. And then we have cos 180 degrees. Why 180 degrees now for that theta? Because it's acting in the opposite direction of the displacement of the object. Now at this point, you simply need the aid of your calculator. So if you punch this part here, from here all the way up until there, you get 833,000. And then minus, if you punch this part here, you get 605,975.2955, right? Which if you further calculate there, subtract the 2, you will get your W net as 227,024.7045, and then joules, right? So note that that's how you were supposed to calculate that one. Note that. So a bit of a stretch there, but then you only just have to check that you put everything correctly, you substitute everything correctly into its own position, and then the rest of that is just your calculator work. Now 5.4, the last question that we have there, is saying 5.4, they are saying along the curved section BC, the kinetic energy of the roller coaster decreases by 108,950 joules. The brakes are then applied at point C, right? So along the curved section BC, the kinetic energy of the roller coaster decreases by 108,950 joules. The brakes are then applied at point C, and then it comes to a stop at point D. Calculate the magnitude of the average braking force required by the braking system to bring the roller coaster to a stop at point D. Use energy principles only. So with this question here, let's start by finding the change in kinetic energy between point B to C, right? So between point B all the way to point C here. And then we can find that by simply saying the EK at C minus EK at B, right? Now they said between B to C, there was a decrease, right? So along the curved section BC, the kinetic energy of the roller coaster decreases. So there was a decrease in the change in kinetic energy between B to C. So the decrease can be indicated by negative. So it's negative 108,950, right? But then what is the EK at C? We don't know the EK at C, right? But then we do have the EK at B because we did calculate the W net between point A to B, right? So that would be the EK at B. So that's the one we got from the previous question, 227,000 and 0.705, right? Now we can use that to find the EK at C by saying EK at C is negative 108,950 plus 227,024.7045, right? And then the EK at C will give us what? 118,000 074.7045, and then joules, right? Now that we have that, we can simply use the work done by non-conservative forces and then say change in EP plus change in EK. But then this will be between point C to D. Let's indicate. This is between C to D because we are trying to bring it to a stop at point D there. Right. Now, if we are to draw a free body diagram of what will be taking place here, this will be the FK in that direction and also the force of the brakes in the opposite direction. So F brakes, right? So this will be our horizontal forces acting from point C to D. The work done by FK and the work done by the force of the brakes, which are both what? Non-conservative forces. Non-conservative forces. Note that the force of the brakes is similar to the force being applied, right? So this force is being applied in order to oppose the direction of the moving object there, the roller coaster. Now, the work done by NC will be replaced by work done by force of the brakes plus work done by FK. Now, changing EP between this point here will obviously be 0 because there is no height here. So we can just replace this by 0. And then changing EK, this will be the EK at D minus the EK at C. Right. Now, we are to further break down this one. This becomes F of brakes will be FB delta X and then cos theta. But then FK once again will be mu K and then mg. Because right now, if we are to calculate the FK at this point, understand that if we are to draw this, our vertical forces, this will be our normal force, and this will be our Fg. To calculate Fk, it's always mu K times N, but then your normal force here on the horizontal surface is equals to Fg. So that's mu K times mg, right? So hence we have this. But then delta X cos theta. This is 0. What's the EK at D? The EK at D will be 0 because the velocity at D is 0, right? Remember, it comes to a stop at D. So this here as well has to be 0. Then minus EK at C. We did find the EK at C right there. There we go. So that would be minus 118,074.7045. Okay, now we are looking for this. Let's substitute FB. Our delta X between C to D is 50. And then this is cos all of these two forces that are acting horizontally are going in the opposite direction of the displacement. So they both have to have 180 degrees. Now the Mced does not change. They say the coefficient of the kinetic friction of the track. So the whole track here, all the way from point A to point D, remains 0.42. So 0.42. But then we know the magnitude of the friction obviously wouldn't be the same. The friction on the incline is not the same friction on a horizontal plane. Then mass is 850, 9.8, while delta x is 50 this time around, and then cos 180 degrees, equal to negative 118,074.7045. Right. Now, if you punch this into your calculator, so here you get negative 50 FB, and then this here will give you negative 4,930 is equals to negative 118,074,7045. Then now we can take this value here and transpose it over to that other side. Negative 50 FB is equals to, if we transpose it over to the other side, we have positive 56,855.2955. And then divide both sides by negative 50. That means the force of the brakes, F of brakes is equal to negative 1,137.106 newtons. Now we understand why it is negative, because it is acting in the opposite direction of the motion. But then we then need to conclude and say therefore, the force of the brakes is actually 1,137.106 newtons, right? So that was an interesting question. for 7 marks. So yeah, pretty tough one there. But then that's how you could have solved that one for a total of 17 marks for the whole question. So yeah, make sure that you stay alert for this type of questions here, and then you do your means to practice as much as possible, just to make sure that you are ready for the final exam. So always note that your prelims are a bit much more difficult because they're trying to prepare you for the final exam. Let's now move to question 6, our Doppler effect. All right, so we have question 6 on Doppler effect. It says a train diver records the frequency of ultrasound waves emitted by a dolphin when the dolphin, which is swimming at a constant speed of 20 meters per second, approaches the stationary diver. The recorded frequency is 253.38 kilohertz. Note that. So this is not in the desired SI unit. We normally have our frequency in hertz, not kilohertz. So that means kilo, we still need to multiply this by 1000. The dolphin passes the diver, and when swimming away from the diver, the recorded frequency is 246, meant to say, 0.71 kilohertz, right? Again, not in the desired SI unit. Then 6.1 says state the Doppler effect in words. Now, to define that, we know the definition of Doppler effect says that it is the apparent change, the apparent change in the frequency detected on the frequency of the sound detected by the listener detected by the listener because the sound source and the listener, the sound source and the listener have different velocities relative to the medium of sound propagation. Right. So that's the definition right there for 2 marks. The apparent change in the frequency of the sound detected by the listener because the sound source and the listener have different velocities relative to the medium of sound propagation. Now, this is very simple because you always know for this topic here, this is the only ever definition that you will have to define. So you walk into the exam, you must know the definition of Doppler effect. Then 6.2 says, use the information given and calculate the speed of sound in seawater, 6 marks. Now, for 6-mark questions, we know that they usually involve having to use simultaneous equations. So here, as we are reading here, we have 2 situations. We have a situation whereby the dolphin is approaching the stationary diver, and then also a situation whereby the dolphin is passing away from the stationary diver. Right. So that means we can start by situation number 1, when the dolphin is moving towards the diver. So we always know with this formula, FL, V plus minus VL over V plus minus VS, and then times FS here. We know that if we are moving towards, I always made you to remember the arrow going up, and then plus upward, and then minus downward, right? So frequency of the listener, we are told that the stationary diver records 253.38 kilohertz. So which we are going to multiply by 1,000, and then this is going to give us 253,380, right? And then is equal to, remember, the velocity of the listener is 0, so we're just going to have V there. But then since the minus is down here, this is V minus. What's the velocity of the source? We are told that when the dolphin, which is swimming at a constant speed of 20 meters per second, so the dolphin is the source swimming at 20 meters per second. Now, we also don't have the frequency of the source, we are not told. But then here we can make the frequency of the source the subject of the formula by simply cross-multiplying here. So if we cross-multiply like this, frequency of the source will be 253,380 times V minus 20, and then over V. And then we want to call this equation number 1. Right. Now, for a case whereby it's now moving away, so we're just gonna leave it like that with Fs being the subject of the formula. In a case whereby now the dolphin is moving away from the stationary diver, this is frequency of the listener. Now arrow will be facing downward, plus down here. So it will be plus down here and minus up there. So this is again V plus minus VL over V plus minus VS times Fs. Now, frequency of the listener, we are told that when it's moving away, it's 246.71 kilohertz, which we want to multiply by 1,000 to give us 246,710. And then is equals to V over, remember, velocity of the listener is still stationary, but then we have a plus down here now, plus 20. And then times Fs. Now let's make Fs the subject of the formula once more. So Fs cross multiply this. This is 246,710 multiplied by V plus 20, and then over V. Now we want to call this equation number 2. At this point now, what you need to do is obviously try to equate the two equations here and do your maths, right? So from here, equate equation 1 and equation number 2. So that's because they are both equal to frequency of the source. So that means you can equate them. So 253, 380, and then V minus 20 over V is equals to 246, 710, and then V plus 20 over V. Now, they both have a denominator of V, so that means we can cancel off this V here by simply multiplying both sides by 1 times V. 1 over V times 1 over V, so cancel off that V there. So that's 253, 380 times V if we now foil inside here. Then if we take the same number multiplied by 20, I'm getting 5,067,600. And then here, this is 246,710 V. So I'm still doing this. And then this number here multiplied by 20, that's 4,934,200. Right, so if we take this, and then in that, these are like terms. Let's say this minus that is going to give us 6,670 V. And then if we take that minus plus this, because if it jumps over there, it becomes positive. So it's the 4,934,200 plus the 5,067,600. This is giving us 10,001,800, right? Then 6,670 divided by 6,670. Our V now is going to be 1,499.52 meters per second, right? So that's the speed of sound in seawater. That's the speed of sound in seawater we have just calculated. Awesome. Okay, so all that for 6 marks, we can see how you were supposed to work that out in simultaneous equation. So you make Fs the subject of the formula in both equations, and then you just have to equate those two equations. Then from that point, it's just your math skills. Then 6.3, if the dolphin's constant speed increases to 25 meters per second instead of 20 now, how will the frequency of the ultrasound waves emitted by the dolphin compare to the waves emitted when swimming at 20 meters per second? Write down only higher, lower, or remains the same. Give a reason for the answer. Now, obviously, for this question, we should say it remains the same. Remains the same. Now, what's the reason for that? The speed has nothing to do with the frequency, right? So they say, how will the frequency? So the speed does not affect the frequency emitted. So that's your reason there. So the speed does not affect the frequency emitted. So they were saying, how will the frequency of the ultrasound waves emitted by the dolphin compare to the waves emitted when swimming at 20 meters per second? This the frequency of the source is not being affected by the speed, right? So the speed cannot affect that. But then the speed can affect the frequency that is being observed or detected. But then remember here, they're asking about the frequency of the source. So the frequency of the source will remain the same. Okay, then now that's how you were supposed to tackle that. It was a very short question, only for 10 marks. Then now let's proceed to question 7, which is your electrostatics Coulomb's law. Okay, let's look at question 7, electrostatics. We are told here, the diagram below shows two small identical metal spheres, R and S, each placed on a wooden stand in a vacuum. Sphere R and S carry charges positive 6 microcoulomb and positive 2 microcoulomb, respectively. Spheres R and S are brought into contact for a while and then separated by a distance of 8 millimeter between their centers. Now we know that our distance should always be in meters, so that there needs to be a conversion there. 7.1 says, which sphere loses electron? Write down R or S. Now when it comes to this, we must understand the concept of which one is electron deficient and which one is an excess of electrons. Now we always know that the one, if we have to look at this in terms of a number line, going to the negative, let's say these are the electrons, and going to the positive, these are the protons. So that means if it has more protons than electrons, it is electron deficiency because of the more protons than the electrons. If it has more electrons than protons, it is an excess of electrons. So in this case, that means if we are to compare positive 2 and positive 6, which one is much more closer to the electron side? It is obviously positive 2. So positive 2 here has far more electrons than a sphere R, which has a charge of positive 6 microcoulomb. Right, so this here represents the one that is electron deficient because it has more protons. So this one is electron deficient. But then S compared to R has excess, right? So it has excess electrons. So meaning in this case, if we are to take these two spheres and bring them together, it is always the one in excess that loses electrons to the one that is electron deficient. So to answer this question, which sphere loses electrons? It is sphere S because it has an excess of electron and therefore it will lose its excess electrons to R, which has a deficiency of electrons. So 7.1 is supposed to be sphere S. Then 7.2 says draw the electric field pattern due to sphere R and S, right? So due to sphere R and S, then we can see they are both positive, and even if we were to bring them together and separate them, they would still be both positive. So that means this represents a repulsion of the two, right? So with the repulsion, this is how we will indicate that. So indicate your fill lines like that. So you don't need to show a lot of fill lines, just a few, so that they do not touch or cross each other. Right. Then, so because it's positive, you have to show that the charges are outward. So charges have to be outward, like that, because charges are always flowing outward from the positive charge, and then that's how you go. That's how you would indicate that. And then we can see that they will not touch here, indicating that they are repelling. So this is something that you need to have there. Those electric field patterns need to be somewhat like that. Then 7.3 says calculate the new charge on sphere S after contact with R. Now, the formula to calculate new charge, we know it's Q new is equals to Q1 plus Q2 over 2, right? Now, what is Q1? We know that we are supposed to write this as times 10 to the exponent of negative 6. It's microcoulomb. So this is 6 times 10 to the exponent of negative 6 plus 2 times 10 to the exponent of negative 6 over 2, right? Now, when you punch that into a calculator, you get positive 4 times 10 to the exponent of negative 6 coulombs. So this is your new charge. And therefore, what does it mean? It means that QR is now 4 times 10 to the exponent of negative 6 coulomb, and also QS is 4 times 10 to the exponent of negative 6 coulombs. Remember, after they are brought together and then they are separated, they now have the same magnitude of charge, right? So that is the law of conservation of charge that takes place here. Okay, now 7.4 says calculate the number of electrons transferred during contact. Now, always be careful about this question here. Remember, we did note that R now will be 4 times 10 to the exponent of negative 6 coulombs. And then also this one, 4 times 10 to the exponent of negative 6 coulombs. Because now at this point, we understand after they've been brought into contact and separated, they now share the same magnitude of charge. But then if you want to calculate the number of electrons transferred, it's up to you. You can either reference based on R or you can reference based on S. Now I'm going to do both of them so that you understand how to do them, right? So suppose I want to reference based on R, then I will start by writing the formula N is equals to change in Q and then over E, right? Now the change in Q means it's the Q finally that's the Q finally minus the Q initially over E, which is a constant. Now what is the Q finally? This is the new charge, so which is 4 times 10 to the exponent of negative 6 minus the old charge Qi was 6 times 10 to the exponent of negative 6 over, now the E there would have to be what? Would have to be negative 1.6 times 10 to the exponent of negative 19. So if you can just go and check this out, it is there in your formula sheet. It is the charge on electron, right? So the data sheet shows it as charge on electron, and then it always has a value of negative 1.6 times 10 to the exponent of negative 19. It is a constant. Now, the reason I'm substituting it as a negative here is because when I subtract what's up here, it will give me a negative. So when I punch that, up here, I'm supposed to have negative 2 times 10 to the exponent of negative 6 over negative 1.6 times 10 to the exponent of negative 19. So the n here should always be a positive integer. So this will give me 1.25 times 10 to the exponent of 13. Then I'm supposed to say electrons. So the 1.25 times 10 to the exponent of 13 electrons that were transferred during the contact, right? Now, suppose someone chose to reference based on sphere S. Again, its n is equals to change in Q over E, and then this is supposed to say Q final minus Q initial by E. Q final is 4 times 10 to the exponent of negative 6 minus 2 times 10 to the exponent of negative 6 over, now the E here, note, because when we subtract this in the numerator, it will be a positive. It affects the sign on my E. Now I have to substitute that as a positive as well, because my n should always be a positive integer. Now from subtracting this, I will get positive 2 times 10 to the exponent of negative 6 over positive 1 times 6 times 10 to the exponent of negative 19. So if I were to punch this, I still get the same answer, 1.25 times 10 to the exponent of 13 electrons. Now it's up to you which sphere you choose to reference from, but then at the end of the day, you're going to end up with the same exact answer. All you have to note is that the condition whereby you need to substitute this as a negative or as a positive. If your denominator will be a negative, then put this one as a negative, because negative divided by negative will give you a positive. But however, if it's positive on the numerator, then substitute it as a positive, so that now you have positive divided by positive is still positive. So always maintain that your n here should be a positive integer. And then that's how you were supposed to get the 3 marks there. Okay, nice. Then let's go to 7.5. It says point X is located 2 millimeters to the right of sphere S1 as shown below. Define the term electric field at a point in width. So we know that they always bring the definition up. If they do not ask you to define Coulomb's law, then definitely that's the other definition that they can ask you to define. Or if the examiner is a bit angry at that on that year, then they can just ask you to define both of those. They can give you Coulomb's law, and then they also ask you to define electric field at a point. So, okay, what is electric field at a point? We say this is the electrostatic force, the electrostatic force experienced per unit positive charge placed at that point. Right. So it's the electrostatic force experienced per unit positive charge placed at that point. Right. For 2 marks, that's how we have it. Now, 7.5.2 now is saying calculate the net electric field strength at point X due to the spheres R and S after R and S have touched and separated. So note that they say after they've touched and separated, meaning these charges here do not apply. So this is always the catch with these questions. You'll find learners still applying these charges, but then here they clearly state that after they have touched and separated. So that means your R now, you have to use the new charge that you calculated, which is 4 times 10 to the exponent of negative 6 coulombs. And also for S, that same new charge, because remember, they now have the same magnitude of charge. So you no longer use the 6 and the 2. Okay, so now we do understand that when it comes to calculating the electric field at a point, all the charges must be in reference to the point charge. So this will be the relationship of sphere R all the way to point X, and the relationship of sphere S all the way to point X. But then X here is a point charge, and a point charge is always positive, right? So now the first thing that we do here is let's try to draw the free body diagram indicating the forces or the electric field that is experienced by point X due to the two spheres. Now, this is a positive charge, and that also is a positive charge. But the point charge again is a positive charge. Now, where we have a positive and a positive, we have repulsion. So we can indicate that this will be X due to, so this will be the electric field of X due to R, right? Because if you check it in reference to X, it will be repelled, right? Because it's experiencing a positive charge from here, and then also it is positive, so it needs to be repelled. But then also again with S is positive and X is positive, so we have to experience another repulsion. So now this is E of X due to S. Now, why am I making this one longer than that? It's because the shorter it is from the point charge, the more electric field it will exert on the point charge, right? So here there is a greater electric field between the two as compared to that one whereby there is a larger distance between the two charges, right? So, okay, that means in order to calculate this, let's start by saying, let's calculate E of X due to R. And then we're going to say E, let's name it E1. Then this will be KQ QR over R squared. Now that means I will have 9 times 10 to the exponent of 9. And then the charge I'm going to use 4 times 10 to the exponent of negative 6. But then the distance in between, I have to note it's 8 millimeter and this 2 millimeter, which will give me 10 millimeters, right? But then remember, millimeters, 2 meters, because our distance should always be in meters. Now, how do we convert that just simply say times 10 to the exponent of negative 3. That's more like dividing by 1,000, right? So 10 times 10 to the exponent of negative 3, and then square that. If you punch that into your calculator, you get 3.6 times 10 to the exponent of 8 Newton per Coulomb. Note that this is electric field. It's not in Newton. It's in Newton per Coulomb, right? Because electric field is simply F over Q. So that's Newton for the force and then coulombs for the charge, which gives us our Newton per Coulomb. Now let's calculate E of X due to S. So we will name this E2. So this will be KQS over R squared by K, 9 times 10 to the exponent of 9. This is always a constant. And then QS, again, it's 4 times 10 to the exponent of negative 6. But then what's the distance between X and S? So between this sphere and that point charge is 2 millimeters, which if we divide by 1,000, it will be 2 times 10 to the exponent of negative 3. And then square that. Okay, so now when we punch that into our calculator, we get 9 times 10 to the exponent of 8 Newton per Coulomb. Now you understand why I had the length of that one longer than this one. So the distance, the shorter the distance, the greater the electric field. But then the longer the distance, the smaller the electric field, as you can see from here. Now, if I want to calculate the E net, because they're all going in the same direction, and then I choose my right as positive, let me say I choose right as positive. So this is going to the right, and then also that one is going to the right. So this will be E1 plus E2. Then it's just a matter of saying 3.6 times 10 to the exponent of 8 plus the 9 times 10 to the exponent of 8. Now, if you add those ones together, you get 9.36. Okay, this one is supposed to be to the exponent of 9. Sorry for that. So this is exponent of 9. So this is 9.36 times 10 to the exponent of 9 Newton per Coulomb. And then to the right. Okay, so pardon me for that. Was just mistake in the way I wrote it. Okay, so that's how you were supposed to calculate that one. 5 marks, and then the whole of the question was for 16 marks. So make sure that you check out your Coulomb's law. I'm aware that in your grade 12, your teachers might not be teaching you this because they'll just say you need to recall it from your grade 11. So it is very important that you go back to your grade 11 and try to revise Coulomb's law, because as you can see, it holds a decent marks there. So that's quite some good looking marks. Sometimes you can find that it's about 20 marks, right? So you can't lose all those marks. Make sure that you do your revision properly. Okay, but then now let's go to question 8, electric circuits. Right. Okay, so now we have this question here on electric circuits. It says grade 12 learners conduct an experiment to determine the internal resistance of a battery. They connect the battery to a rheostat on an ammeter and a voltmeter as shown in the diagram below. The results obtained are shown in the diagram below. Now, as we can see, this is a graph of current versus potential difference. So they kind of inversed it from the one that we know, because we are mostly used to the one whereby we have current and potential difference there. We are used to the potential difference versus current. But now they inversed it to say current versus potential difference. Now, always make you note that be careful of that graph, because the one that you know is potential difference versus current, but then sometimes they can inverse it. And if they inverse it, it changes a lot of things. Now, EMF of the battery, remember we said On the one that we are used to, we used to find the EMF right here. But now we can't say this is the EMF because what do we have on the y-axis? It is the current. So what we have here is the potential difference, and we know EMF is the potential difference when no current is flowing. So it would have to be represented by the x-intercept now. Right. So the x-intercept would have to represent the EMF of the battery. But then with the potential difference versus current, the y-intercept is the one that represents the EMF. So always note the difference there. If this was current here, and then a potential difference here, and then we had the same graph like this, now the y-intercept would be the EMF. But then now, because we have potential difference here and current here, now, where do we find the EMF? At that point. So the EMF of the battery is what? 12 volts. So 8.1.1, we are going to say 12 volts. Now, the lost voltage when the current is 2 amperes. When the current is 2 amperes, we are looking for the lost volts. So where is current? Current 2 amperes. So we're just going to go like this, and then there we go, we have the 8 there. But then remember, we are not looking for the V external. The 8 here is representing the V external. But then since we know that EMF is the sum of the V external and the V internal, we know that if EMF is 12 and the V external is 8, that means the V internal, we can simply get it by saying 12 minus 8. And then our V internal will give us 4 volts. So for this one mark here, we are supposed to say it's 4 volts. Right, so note that. Okay, 8.1.3 says the internal resistance of the battery without using the equation E is equals to I bracket R plus R in your calculation. So if you are not supposed to use that, you must make use of the gradient, right? Now you will remember that I said if you have the one that we are used to, potential difference versus current, then our gradient always represents the resistance, negative R, right? But then if now you are given this here, that means your gradient would have to represent the inverse of the gradient. It would have to represent the inverse of the internal resistance, because what did they do? They inversed the graph. So if you want to have a look at that, check. We have a gradient will be equals to the change in the current over the change in voltage. So change in Y values over the change in X values, right? And then obviously, if we are to use the last point here, we will have the current there will be 6 minus 0, and then over 0 minus 12, right? So this will give us a negative 6 over 12, which is negative 1 over 2, right? So this will be our gradient. But then note that we are used to R being equals to V over I. Not R is equals to I over V. So whenever you have R, whenever you have I over V, meant to say, this actually means that what you have is R to the exponent of negative 1. It's the inverse of the resistance, so which is equals to I over V, meaning that if we take that our resistance is the internal resistance, that would have to represent the inverse of the internal resistance. So if we say our gradient here is representing the inverse of the internal resistance, negative inverse of the internal resistance. Why? Because this is a decreasing line, so it has to have a negative gradient. So this is negative 1 over R is equals to negative 1 over 2. Now at this point, we do understand what needs to be done. We can just divide both sides by 1 over 2. Divide both sides by negative half, or maybe let's multiply both sides by negative 1, and then this is 1 over R is equals to 1 over 2. And then if we are to inverse this like this, our R will become 2 ohms. right? Then that's our internal resistance right there. Okay, so that's all you needed to do without having to apply this formula here. You needed to use the gradient, but then understand that the gradient has been inversed to the inverse of the internal resistance. Okay, so now let's continue. Now let's see the electric circuit. In the circuit below, the battery has an EMF of 19.125 volts. So this is the EMF right there. And internal resistance of 0.5 ohms. Voltmeter V is connected across the battery. And then ammeter A1 and A2 and the connecting wires have negligible resistance. Define the term EMF in words. So we know that you must expect this definition. Either expect the definition for EMF or current, or they can make you define the Ohm's law. So the maximum energy provided by a battery per coulomb of charge passing through it. Right, so note that definition there. So definition for EMF, it says the maximum energy provided by a battery per coulomb of charge passing through it. And that for 2 marks. Okay, now 8.2.2 says, what is the reading on voltmeter V while the switch is open? While the switch is open. When the switch is open, that means voltmeter V here goes directly to the battery, right? So if you are to indicate, this is voltmeter V, and then that means the connecting wires to voltmeter V will go directly to the battery, meaning it will be reading the voltage of the battery. But then what is the voltage of the battery? We know the voltage of the battery is the EMF. So that means voltmeter V there will be reading the EMF when no current is flowing. So that means what will be the reading there? It has to be 19.125 volts, right? So note that. Guys, always refrain from saying it is 0. It would be 0 if we were to connect the voltmeter to one of the resistors here. Let's say we'd had a voltmeter there, and then we say current is not flowing here. So obviously, because current is not flowing here, then that means no potential difference driving the current. So that means the voltage there would be 0. But in this case, this voltmeter is directly connected to the battery, so it means it will read a particular voltage, which is called the EMF. That is the potential difference of the battery, the maximum potential difference. Then switch S is now closed. The reading on V decreases by 6.5 volts. Now, whenever they tell you about the voltmeter decreasing, that 6.5 volts automatically, we know that is the internal voltage, right? So remember, the minute we close the switch, then some of the voltage has to be lost in a way. So they call it the lost volt. So it has to be lost so as to heat up the battery. So this is happening because of the internal resistance in the battery. Now they say calculate the current flowing through the battery for 3 marks. Now you can tell that it should be an easy question, 3 marks formula, substitution, correct answer. So all we are supposed to do to calculate that one, simply use the formula. So for 8.2.3, going to say V internal is the current multiplied by the internal resistance. Now the V internal, we noted that if it says it decreases by, so that value in which it decreases by goes to the internal voltage. So it's indicating the internal voltage. Then we are looking for the current, so I, but then we do have the internal resistance we were given up here, 0.5. And then we are also shown here, so 0.5. If we divide both sides by 0.5, then our current is supposed to be 13 amperes, right? So 13 amperes, correct. Now 8.2.4 says calculate the reading on a ammeter A1, right, on ammeter A1. Okay, so now let's check that one out. So A1 has to be the current over here. So now that we have found that the total current is 13 amperes, then how do we find that one there? So we can simply say for 8.2.4, let's first indicate the current flowing like this. So this is the positive terminal. Note that this one is now closed here. So the current is flowing like this, but then when it reaches that point, that is now the parallel branch. So your current has to split here. Then some current splits and goes that way. Some of the current splits and goes down here, and then flows through R. And then which we have A2 reading the current of R there, then goes like that. But then here, within that parallel branch, there is still yet another parallel branch. So which is now dividing this current here. Then the current now goes like that. So note the color scheme strategy there. Where you see the same color, that means they share the same current. If you see the same color, they share the same current. Okay, so this is what we have. Now, we have 13 amperes which should be split in here, and then we are supposed to find A1 then. Now, what we can try to calculate here is that we can say here we have the parallel resistors in this branch here, which we can say R parallel is equals to R1 times R2 over R1 plus R2, the product over sum. Then this is 5 multiplied by 2.5 over 5 plus 2.5. And then now, the resistance that we get from there is 1.67 ohms, which if we understand here, note that the green current here splits here to form that blue current there. So here I was supposed to indicate with a different color, because the current in here will not be the same as that one. They don't have the same resistance. They don't have the same resistance. Right. Okay. Now, let's continue. Okay, so now that the current is split there, we understand that the current that is splitting among the 5 ohm resistor and the 2.5 ohm resistor is this current here, right? So that means if I were to combine the current over here and the current here, it will give me the total current that's flowing through A1, right? So the current over here plus the current here will give me the current through A1, which will also be equal to the current in the 10 ohm resistor. So meaning in other words, if we have to take this one as a bundle, it is actually in series to the 10 ohm resistor. If we are to take this one as one resistor, one bundle of a resistor, which is 1.67 ohm, then it is actually in series to the 10 ohm because it shares this green current here. Look at the color scheme. So remember we said if we add the blue here and the pink here, then this is supposed to give us what? It's supposed to give us this current. So that means the current here combined is equal to the current of the 10 ohm resistor, making this one to be in series because in series the current is the same throughout. So meaning if we are to calculate the total resistance over this branch here, this is now R is equals to 1.67 plus the 10, which is giving us 11.67 ohms. Right. Now, having that, we can now calculate the V parallel over there by saying, so the V parallel is 19.125, which is the EMF, minus the internal resistance, which is 6.5. And then we are going to get 12.625. right? And then note that everything in here that we got is actually connected in parallel, right? So to calculate the current over there, we will then say, therefore, R is equals to V over I, right? Then to calculate the current, it's I is equals to V over R, the V parallel over the resistance over there. Now, V parallel is 12.625 over the R. We are going to substitute the 11.67 because we are looking for which current? The current over here. So we do understand that since this here is the parallel branch, the voltage combined for this part here would have to be 12.625 volts, but then also the voltage for this one here, resistor R, will also have to be 12.625 volts. Why? Because in parallel, we say the voltage is the same throughout. Now, if we are to divide that, we get a current of 1.08 amperes. Right? So that's how you were supposed to go about answering that one for a total of 4 marks. Right? So note that we first calculated the R parallel over here, which we then combined to that one to give us 11.67. But then now we calculated the voltage of the parallel simply by taking our voltage of the parallel as the V external. So EMF, remember, is V external plus V internal. If our V external is V parallel, then we simply need to take the EMF minus the V internal to get the V parallel. And then that's what we did here. From that, we then wanted to calculate the current. So we already have the resistance, we already have the voltage, and then we can calculate the current. Voila, 1.08 amperes. Okay, then 8.2.5 now is saying the value of the unknown resistor R. We must now calculate the value of the unknown resistor. Now, to calculate that, it's pretty much simple. Now that we have got that, we can use the formula for 8.2.5. Use the formula E is equals to I, and then R external plus R internal. Our EMF, remember, 19.125. The current, which is the total current, remember, this is always IT, the total current. And then R external, we don't know yet, because remember, we did not include this one when we were calculating. Then the internal resistance is what? 0.5. Now, in order to calculate this, we need to say 13 both sides. And then if we divide those 1.47, and then we have R plus 0.5. If we transpose the 0.5, we now have 0.97 ohms, right? So this is our R external. So to then calculate here, we can say 1 over R external, because we said all the resistors here are actually in parallel. This is 1 over R1 plus 1 over R2. Now the R1, we're going to take it as this whole branch here. This whole branch here. So that's 1 over 0.97, 1 over, we did calculate it's 11.67. So the R2, we are going to take it as this R only. And then now it's just 1 over 0.97 minus 1 over 11.67 is equals to 1 over R. Now we know what to do. We need to then inverse the solution to this. So you can just punch it all together like this inside the bracket to the exponent of -1. Then your R will become 1.06 ohms. Right. So, and that's how you are supposed to calculate that one. Okay, so now we have 8.2.5. It says, how will the reading on voltmeter V be affected? They say an unknown resistor R is now replaced by a conducting wire. So let's try to do what they're telling us here. So they say the unknown resistor R is now replaced. So it's now replaced. So this is now being replaced by a connecting wire like this. So it's no longer there. Right. Now they're saying the unknown resistor is now replaced by a conducting wire of negligible resistance. How will the reading on voltmeter V be affected? Write down increase, decrease, or remain the same. So this is what we are supposed to tell them. Note our format, the observation. What's the observation? What will happen to the total resistance if we remove that? The total resistance of the circuit decreases. Right. So if you are removing that, the total resistance of the circuit decreases. Now, the current increases because we know our relationship of R is inversely proportional to current. So if the total resistance decreases, the current increases. Now, we know that according to E, EMF is equals to I, R plus R. If the current increases, the V internal increases and the V external decreases for a constant EMF, to maintain a constant EMF. So what is our answer? Therefore, voltmeter V decreases because voltmeter V is actually reading the V external. Right, so therefore voltmeter V decreases. So our answer to this one should be decrease. That's how you were supposed to tackle that question there. So all in all, we had our electric circuits for 23 marks. So also, this is another topic that you should pay attention to when it comes to your revision. Make sure that you master this topic so that you grab your marks. And then now let's go to our question 9. So our question 9 in this case was photoelectric effect. And then it happened to be the final question of the exam. Okay, so now we have question 9. It says an experiment is conducted to investigate the relationship between the wavelength of light incident on a metal and the maximum kinetic energy of the emitted electrons from the surface of the metal. The graphs below, not drawn to scale, represents the result obtained. Then we have 9.1. It says define the term photoelectric effect. So what is photoelectric effect? We are going to say this is the process whereby electrons are emitted from a metal surface, when light of suitable frequency is incident on that surface. Right. So also other definitions that you need to check under this topic, it's your work function and your threshold frequency. Then 9.2 says write down the value of the threshold wavelength for the metal used. Now we can see that our x-axis here is indicating the wavelength, and if we are looking for the threshold wavelength, that means it would have to be indicated by the x-intercept here. So the x-intercept would have to indicate the threshold wavelength. So our threshold wavelength is equals to 5.5 0.40, but then you don't just write it like this. You need to also consider that there's times 10 to the exponent of negative 7 here, which is indicating that each and every value here has to be raised to that exponent there. So times 10 to the exponent of negative 7 meters, right? And then 9.3 says calculate the maximum speed of the ejected photoelectrons when the kinetic energy is x. So, okay, to deal with that one, we obviously need our main formula here, which is E is equals to the work function plus the EK max. And then we know in order to break this one down, this goes hc over lambda because we are given the wavelength, right? We are not given frequency. So if we are given wavelength, we have to break down the formula like that. Then also our work function will be hc divided by the threshold wavelength. And then for EK max, we have half the mass of the electron and then V squared max, right? So let's substitute in our constants. We have 6.63 times 10 to the exponent of negative 34, and then C is 3 times 10 to the exponent of 8. Now the wavelength that we are going to use, remember we are calculating the maximum speed of the ejected photoelectrons when the kinetic energy is x. Now what would be the wavelength at that point? So the one that corresponds to the x there, the wavelength is 3.20. So that is the wavelength of the light that has been used. So 3.20 times 10 to the exponent of negative 7. And then it's equals to, as relating to the metal surface, then this is the information that we have. So the threshold wavelength is 5.40 times 10 to the exponent of negative 7, right? So note that this is the wavelength of the light that has been used, and this is the wavelength that is required by the metal surface in order to eject the electrons, right? So plus half the mass that we are using here is the mass of the electron. It is found in your data sheet with a constant of 9.11 times 10 to the exponent of negative 31 kg. Then we are looking for the V squared max there. Now, all we need to do right now is simply take this and transpose it over to the other side, and then do our maths quickly there. So this is 6.63 times 10 to the exponent of negative 34, and then times 3 times 10 to the exponent of 8, and then 3.20 times 10 to the exponent of negative 7 minus this here. So 6.63 times 10 to the exponent of negative 34, and then 3 times 10 to the exponent of 8 over 5.40 times 10 to the exponent of negative 7. And then in order to get that, so it's equals to V squared max. Now at this point, you'd have to divide everything throughout by the half 9.11 times 10 to the exponent of negative 31, right? And then after you have got the solution to that one, you simply square all of this, right? So just to avoid rounding off, this is what you would do here. So if you are able to just punch all of this at once in your calculator, then you'd find that your Vmax is actually equals to 700 or 7 point, let's keep it into the scientific notation, 7.4561 times 10 to the exponent of 5 meters per second. Now, if we just round off to 2 decimal places, that's 7.46 times 10 to the exponent of 5 meters per second, right? And that's how you would find your Vmax like that. So always have this easier approaches to just dealing with everything all at once. But then if you want to do it step by step, you can still do it step by step. Just know that when it comes to physics, they don't necessarily mark your maths. So more steps does not mean that they will award you marks, because simply they just offer marks for the formulas and the substitution into the formulas, and then the correct answer with the correct SI unit. Now, 9.4 says, how will the maximum kinetic energy of the photoelectrons be affected if light of a higher intensity is used? Write down only increase, decrease, or remain the same. So we know that increasing the intensity of light does not affect the kinetic energy of the photoelectrons. Again, it does not affect the frequency of the photoelectrons that are being ejected. The only thing that it can affect is the rate at which the photoelectrons are being produced, and therefore the rate in which the current will flow. So that's the only thing that it can affect. So here we are supposed to say it remains the same. It remains the same. And then as our reason, we can say intensity of light only affects, so it only affects the number of photons ejected on the metal per second. Right. Or you can simply say intensity of light does not affect kinetic energy. Does not affect kinetic energy. Right, so that's how you were supposed to go about answering that question. So again, it was a short question for only 10 marks. So this question paper here had no electrodynamics, so we just moved from electricity straight to photoelectric effect. It was a total of 150 marks, all for 3 hours. Then that's how you were supposed to go through this question here. And then make sure that you see all your mistakes, you correct those mistakes in preparation for the final exam, and just keep on practicing. Do not relax, guys. You only have a month and so until you sit down for your final exams. So happy practice there. All the best. You know what to do. Press the thumbs up button if you have enjoyed the lesson and then you found it helpful. And if you've been watching the videos and haven't subscribed yet, please smash that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.